So now we have some special case polynomials that make it a little easier for us to factor without doing much work at all. So the first special case is called a perfect square trinomial. Basically, in a perfect square trinomial, your first term would be a perfect square. So a squared would be a perfect square. And then your last term would also be a perfect square, so plus b squared. And now your middle term could be plus 2 times the square root of your first term times the square root of your your last term. If you have a trinomial in this format, then this is a perfect square trinomial. And how we would factor this is we would take the square root of your first term, the square root of a squared would be a. We would take the square root of your last term, which would be b. And we would take the operation between your first and second term, which in this case would be a plus sign, and then we would square that binomial. Now another perfect square trinomial could be that you have the first term's a perfect square, and your last term's a perfect square, and it's still a plus b squared. But this time you have a minus 2 times the square root of your first term times the square root of your last term. To factor this, we would do the square root of our first term, which would be a, the square root of our last term, which would be b, and the subtraction sign in between your first and second term, and then we would square that binomial. Now, this perfect square trinomials are only in these two formats. So if you have a minus sign between your second and last term, then that would not be considered a perfect square trinomial. All right, and then let's actually practice some before we move on to special case number 2. So in number 1, this is a trinomial. We're going to see if it's a perfect square trinomial. The first term is a perfect square. X squared is a perfect square, and if you take the square root of x squared, you get an x. The third term is a perfect square, and it's a plus 9. You take the square root of your plus 9, you get a 3. Now we need, that's not the only criteria here, we need to check our middle term. So how we check our middle term is if we multiply the two square roots here, the x and the 3 together, and then multiply that by 2, we gotta see, does that equal our middle term? Well, a 3 times an x is a 3x, and a 3x times a 2 does equal a 6x. So this is a perfect square trinomial, and now we can factor. You take the square root of your first term, which is an x, the square root of your last term, which is a 3, and the operation between your first and second term, which is a plus sign, and then you square that binomial. That is your answer. You could also write it as an x plus a 3 times an x plus a 3. That's the same thing as an x plus 3 squared. Another thing is if you didn't recognize that this was a perfect square trinomial, this is a trinomial, meaning it has 3 terms and the coefficient of x squared is 1. You could have used the box method to factor number 1 if you didn't recognize right away that it was a perfect square trinomial. Let's look at number 2. We're going to test to see if this is a perfect square trinomial. If we take the square root of our first term, because it is a perfect square, we would get an x. If we take the square root of our last term, we would get a 7. If we multiply those two square roots together and then times 2, a 7 times an x is a 7x, times a 2 is a 14x. Ignoring the sign, we do get our middle term. So this is a perfect square trinomial, and so to factor this, we take the square root of our first term, which was an x, the square root of our last term, which was a 7, and the operation in between my first and second term, which is a minus sign, and we square this binomial. Or you could write your answer as an x minus 7 times an x minus a 7. If you didn't recognize that this was a perfect square trinomial, then what you could have done is you could have used the box method because the coefficient of x squared was 1. All right, looking at number 3, we're going to test to see if this is a perfect square trinomial. Now, while your first term is a perfect square, your last term is not. So this is not a perfect square trinomial, which does not mean that it's not factorable. All this means is that we actually are going to use a different method of factoring. And that method of factoring, first we're going to take out the greatest common factor, which is a 2. And when we take that 2 out, I'm left with an 18p squared plus a 57p minus a 10. And now this is a trinomial with 3 terms. We're going to use the x method to factor. So if you cannot use the perfect square trinomial shortcut, then you will need to use either the box or the x method. So on the top of your x is your a times your c, your 18p squared, times your negative 10, which is a negative 180p squared. And in the bottom of your x is your b value, which would be 57p. I need 2 numbers when multiplied together equal negative 180p squared, but when added together equal 57p. That is going to be a 60p and a negative 3p. So rewriting this as an 18p squared plus a 60p minus a 3p minus a 10, we're going to group our first 2 terms and our last 2 terms. And the greatest common factor out of my first 2 terms would be a 6p. And I'd be left with a 3p plus 10. And I would need to factor out a minus 1 out of my next 2 terms to be left with a 3p plus a 10. We cannot forget when we write our answer to include the greatest common factor, which is 2. And then one of our binomials is going to be the stuff on the outside. And my other binomial is going to be one set of those parentheses. Now notice, if this was a perfect square trinomial, it would have taken seconds to complete this problem instead of using the x method. So if you do have a problem that is a perfect square trinomial, it's actually a lot quicker for you to use the perfect square trinomial shortcut. However, in this case, number 3 was not, so we couldn't have used it. However, in number 4, if we're looking between using the perfect square trinomial shortcut, if it is a perfect square trinomial, or the x method, the perfect square trinomial shortcut would be easier and a lot quicker. Now let's test to see if number 4 is a perfect square trinomial. Well, the first term is a perfect square. The square root of my first term is 3n. My last term is also a perfect square. The square root of 49 is a 7. If I multiply both of those terms together, you get a 21n, and multiplying those by 2, you get a 42n, ignoring the operation. So this is a perfect square trinomial, which means we take the square root of our first term, which was 3n. We take the square root of our last term, which was 7. Let me rewrite that 7. And we take the operation that's in between my first and second term, which is a minus sign, and we square that binomial. Now again, we could have used the x method on this, but it actually was a lot quicker to use the perfect square trinomial shortcut. Let's look at number 5 to test if this is a perfect square trinomial. The first term is a perfect square. The square root of the first term is a 4m. The square root of my last term is a 9. If I multiply both of those things together, 4m times a 9 is a 36, and multiplying that by 2, we do get a 72m, ignoring the operation that comes before it. So this is a perfect square trinomial. So we take the square root of my first term, which was 4m, and the square root of my last term, which was 9, and we take the operation in between my first and second term, and we square that binomial. So again, we could have used the x method to do this, but it was a lot quicker to use the perfect square trinomial shortcut. Again, in number 3, we could not use the shortcut. We were forced to use the x method because this was not a perfect square trinomial. Now, before we move on, because numbers 6 through 9, these are not trinomials, we're going to look at special case number 2. So special case number 2 is called a difference of two perfect squares. So if I was given a perfect square minus another perfect square, and I only have two terms, then this is another special case polynomial. We could factor this into the square root of my first term minus the square root of my second term times the square root of my first term plus the square root of my second term. This is a difference of two perfect squares. Now, if you have the sum of two perfect squares, then you cannot factor it this way. So looking at number 6, both of my terms are perfect squares here. So we can factor this. This is a difference of two perfect squares. How you factor this is you take the square root of your first term, the square root of v squared is v, minus the square root of your second term, which is a 10, and then you do the same exact terms, only you put a plus sign in between those two terms now. This is now fully factored, and if you wanted to check, you can FOIL it back out to see if you were correct. All right, number 7. This is a difference of two perfect squares. So you take the square root of your first term minus the square root of your second term times the square root of your first term plus the square root of your second term. This is fully factored. In number 8, this is a difference of two perfect squares. You take the square root of your first term, which would be a 5d, minus the square root of your second term times the square root of your first term plus the square root of your second term. That is fully factored. Now, number 9, you're probably thinking that this is the 12t and 48 are not perfect squares, which you're correct. However, you should always take the greatest common factor out first. In all the rest of the problems, we didn't have a greatest common factor. But in this one, we do. We have a greatest common factor of 12. When I take that 12 out, I'm left with a t squared minus a 4. And guess what? This is a difference of two perfect squares here. So I'm going to rewrite my GCF, which is a 12, and now I'm going to factor the t squared minus 4 by taking the square root of t squared minus the square root of 4 times the square root of t squared plus the square root of 4. And that is now fully factored. All right, looking at number 10, between all three terms, we do have a GCF of 3. When I take that 3 out, I'm left with a 4x squared plus a 4x plus a 1. We are going to see if this is a perfect square trinomial. Well, taking the square root of my first term, I get a 2x. Taking the square root of my last term, the square root of 1 is just a 1. If I multiply those together, I get a 2x. And times 2, I do get my middle term, which is a 4x. So this, what's left in parentheses, is a perfect square trinomial. We take our GCF and we rewrite it. Then I take the square root of my first term, which was 2x, the square root of my last term, which was a 1, the operation in between my first and second term, which is a plus sign, and I square that binomial. All right, in number 11, let's see if this is a perfect square trinomial. Taking the square root of x to the 20th power, that's an x to the 10th power. Taking the square root of 4y to the 10th power, that's a 2y to the 5th power. Multiplying these two things together, I get a 2x to the 10th, y to the 5th. And multiplying by 2, I do get a 4x to the 10th, y to the 5th, ignoring my sign that's in between. So this is a perfect square trinomial. We did not take out a GCF, so how to factor this is I take the square root of my first term, which was x to the 10th. I take the square root of my last term, which was 2y to the 5th, I take the minus sign and square it. I'm going to have you try 12 through. All right, here are your answers.